You know, in machine learning, speed, it isn't just a nice to have. It's pretty much everything, right? A model that's slow to train or gives a delayed prediction can be the difference between a project succeeding and a project failing. So today we're going to dive in and learn how to make our TensorFlow models absolutely fly.
So let's be real for a second. Is your model actually fast enough? I mean, are you leaving performance on the table? Is your super expensive GPU just, sitting there twiddling its thumbs waiting for data? Or worse, is your training run about to crash because you're out of memory? Yep, those are the exact problems we're here to solve.
You know the old saying, right? You can't optimize what you can't measure. And this is where TensorFlow really steps up. It gives you this incredible suite of tools. Think of it like an X-ray for your model. It lets you see exactly how it's using time and memory so you can hunt down those pesky bottlenecks and get things moving faster. All right, here's our game plan. We're going to start with our diagnostic hub, the TensorFlow profiler. Then we'll jump into how to actually speed things up with software and hardware acceleration. We'll cover scaling across multiple machines, and of course, how you can put all this into practice. Finally, to make it all stick, we'll wrap up with a cool little metaphor, the performance assembly line. Let's do this. Okay, first up, our diagnostic hub, the TensorFlow profiler. This is your command center, your mission control for figuring out what's really going on under the hood. And the best part? It's all built right into TensorBoard. So this is where our detective work begins. So when you first open the profiler, you land on this overview page. It gives you that nice, high-level, 30,000-foot view of your run. But honestly, the absolute killer feature here is the recommendation for next step. It's awesome. It'll often just straight up tell you what's wrong. For example, if your model is input-bound, which is just a fancy way of saying it's starved for data, this page will flag it for you immediately. So useful. Okay, so let's say the overview page did, in fact, tell you that you're input-bound. Well, this is where you go next. The Input Pipeline Analyzer lets you deep dive into your tf.data pipeline. Is your data loading slow? Is pre-processing the culprit? This tool helps you answer that really painful question, why is my expensive GPU doing absolutely nothing? Now, if you need to go full-on forensic investigator, you've got the trace viewer. Seriously, think of this like a super slow-motion replay of everything your model does. It lays out every single operation on a timeline. You can see what ran on the CPU, what ran on the GPU, and exactly how long it took, down to the microsecond. It is the tool for hunting down that one specific op that's slowing everything else down. And of course, performance isn't just about speed. It's also about not crashing. We've all been there, right? That dreaded out-of-memory error. Ugh. Well, the memory profile tool is your new best friend. It shows you exactly how memory usage grows over time, so you can pinpoint the exact moment your code got a little too greedy and pushed the GPU past its limit. All right, we've used the profiler and we've found the problem. Diagnosis complete. Now for the fun part, fixing it. Let's talk about software and hardware acceleration, starting with the code itself and going all the way down to the kernels. So by default, TensorFlow runs your Python code line by line. That's called eager mode, and it's great for debugging. But for real performance, you want graph execution. All you have to do is add a simple @tf.function decorator. This tells TensorFlow, hey, take this function, compile it into a super optimized graph, and then run it. It's like switching from an interpreter to a compiler. And if you want an extra boost, you can enable XLA, which fuses operations together and makes things even faster. Beyond graph compilation, there are a few other software tricks that are just game changers. First, mixed precision. You use smaller numbers, 16-bit floats instead of 32-bit, which cuts memory usage in half and really speeds things up on modern GPUs. And for your data pipeline, using auto-tune and prefetching, look, these are just non-negotiable. Seriously, they make sure your GPU is always fed and happy, never waiting for data. Now, for those of you who really want to get under the hood and squeeze out every last drop of performance, you can dive into hardware-specific tweaks. We're talking about things like tuning the L2 cache on NVIDIA GPUs or managing thread modes to make sure data prep isn't stepping on the toes of your actual model training. It's advanced stuff, but it just shows you how much control TensorFlow gives you if you need it. So, you've optimized everything on one GPU, but it's still not enough. Your model's just too big. What now? Well, now we go distributed. We're going to scale across multiple machines. And TensorFlow's Distribute API is honestly magical. It lets you take your training from one GPU to a whole cluster, often with just a few changes to your code. So you've got a few main strategies to choose from. If you have one machine, but with a bunch of GPUs in it, mirrored strategy is your go-to. It's super simple. If you have multiple machines, each with GPUs, then you'll want multi-worker mirrored strategy. And if you're lucky enough to work with Google's TPUs, TPU strategy is what you'll use for a ridiculous speedup. The whole point is, there's a strategy for whatever hardware you've got. Okay, this all sounds awesome in theory, but I can hear you asking, how do I actually do this? How do I get this profiling data from my own model? Well, good news. It's probably way easier than you think. Let's take a look. It really just comes down to how you're writing your code. If you're using the standard Kerasis.fit method, it is literally one line of code. You just add the TensorBoard callback and you're done. Bam. If you're writing your own custom training loop, it's still super easy. You just wrap your main training step code in this tf.profiler block. That part is really important because it tells the profiler, hey, this is one step, so it can measure everything accurately. Whew. Okay, we have covered a ton of ground, right? From diagnosing problems to fixing them and even scaling them up. So to help make all of this really stick, let's pull it all together with a simple analogy, the performance assembly line. I want you to picture your whole model training setup as a high-speed factory assembly line. And what's your goal? To crank out fully trained models as fast as you possibly can. Every single tool we've talked about today has a very specific job to do in making sure that factory is running like a well-oiled machine. So think about it like this. First, the TensorFlow profiler, that's your inspector walking the factory floor with a stopwatch, looking for slow workstations. Then you've got tf.function in XLA. That's like ripping out the old, clunky machines and installing brand new, super fast ones. Your tf.data optimizations, that's your supply chain. It's making sure the raw materials, your data, show up exactly when they're needed so the line never stalls. And distributed strategies? Well, that's like building a whole new identical factory right next door to double your production. See? It's all part of a system, a cycle. You diagnose, you fix, and you scale. And when you start thinking about performance this way, from end to end, you stop guessing what's slow and you start knowing. And that is how you unlock what your model is truly capable of. So there you have it. You've got the roadmap, you've got the toolbox. You now know how to find every weak link in your own assembly line, and you know how to make it stronger. So the only real question left is, what bottleneck are you going to go crush first?